Okay, guys, let's start chapter 3. Have your guided notes open. Chapter 3 guided notes, and be filling them out as we go through these slides. Chapter 3 is going to be extremely important because it sets up the rest of the year. What we're going to talk about in chapter 3 is Newton's 3 laws of motion. Okay, so we're going to spend a lot of time talking about the different laws of motion. Okay, I've got a picture here. This is Isaac Newton. He has great hair, doesn't he?
Yeah.
He's got great hair. He's got great hair, but guys, one of the smartest people to ever live on the planet.
Self-proclaimed.
One of the smartest scientists and the greatest scientists to ever live on the planet. Definitely in the top 2 or 3. That's for sure. So let's find out why Isaac Newton is so high regarded by a lot of people. So Isaac Newton, he lived from 1642 to 1726. He was an English physicist and mathematician. Regarded as the most influential scientist of all time. He wrote a book called Principia. In that book, Newton laid out his laws of motion, the 3 laws of motion. He laid out universal gravitational law, which we'll talk about later in the year. But we still use, and NASA still uses those equations today to figure out how to land a rover on Mars. Okay, so a lot of the stuff he came up with, in the 1700s, still used today. And many other scientific principles are in that book. It was just a great book in terms of laying out a lot of new science, and that we, in fact, still use today. He developed calculus to help explain scientific principles. Guys, that's why we use math. Math helps us explain science. Here's a scientist. He wanted to be able to explain something that he's observing, and he couldn't do it with the math that existed at that time. So what did he do? What did he do? He developed calculus to help explain what he observed. So just incredibly smart. He was a genius. So let's talk about Newton's first law of motion. You're supposed to write it, are you not?
Yes.
Okay. So Newton's first law says that an object in motion will stay in motion. Its motion will be at constant velocity, and an object at rest will remain at rest. But here's the kicker: unless it's acted upon by a net force. So it's going to stay at rest, or it's going to stay in motion unless it's acted upon by a net force. I always like to use this example. Okay, how long is that going to stay on the counter?
Till we have an earthquake.
It's going to stay at rest until what happens, guys? Unless it's acted upon by a net force. Well, right now there's not a net force acting on it. It's going to stay there forever unless a net force acts on it. Is this a net force? Am I putting a net force on it? Yeah, it's moving. I'm putting a force on it. This first law of motion is also called the law of inertia. A lot of people call Newton's first law the law of inertia. You've watched Bill Nye, right? It's on the intro. Yeah. Well, what is inertia? Inertia is an object's resistance to change in its motion. It's an object's resistance to change in its motion. So inertia, an object's resistance to change in its motion. And here's the thing about inertia. An object's inertia is related to its mass. The more massive an object is, the more inertia it has. So the more massive it is, the more inertia it has. Let me see if I can illustrate this. Say there was a big, huge boulder. I'm going to call this boulder A. And then there's a small boulder. I'm going to call this one B. And here's Dalton. He's trying to push it. Which one is Dalton going to be able to move easier? A. Why? No, that's not true. He's going to be able to move B. Why?
Because it's small.
Because it's smaller. It's less massive. Let me ask you this. Which boulder, A or B, has more inertia? A has more inertia. Why does it have more?
More massive.
It's more massive.
Yes.
This one's going to resist change, right, in its motion more than B, right? Can we see that?
Yeah.
Assuming they're the same density, same material.
Yeah, what if one's aluminum and one's block?
Yeah, assuming they have the same density, the same material. A has more inertia because it's got more mass. Okay? So we can think of inertia like that. Okay, let's back up in time a little bit. Remember, Newton was the 1700s. Let's go, what did they think about motion before Newton came along? So, prior to Newton, the prevailing view on motion was given by Aristotle. Aristotle was a Greek philosopher who lived between 384 BC and 322 BC. So a long time ago. If you took chemistry last year, we talked a little bit about Aristotle, Greek philosopher. But he also thought about motion, and here's what his theory on motion was. It says, according to Aristotle's theory of motion, the natural state of things is at rest. So he said just things naturally come to rest. He said that a force is required to keep something moving at a constant rate. So if you think about this, say you're trying to push this ball across the room. Doesn't that make sense how Aristotle thought about it? Don't you keep, in order for this ball to be in motion, don't you have to keep adding a force?
On Earth,
Okay, good.
because we have gravity
Good.
and friction.
Good.
And heat temperature.
That's right. Good job. But
In space, wouldn't there still be friction?
Unless.
Are we talking about space below on Earth?
so good. Dalton's got it. Dalton's on. I don't know about the rest of us though. Let me explain it. Okay, so Aristotle said that the natural state of things is to come to rest. If you give this a big shove, it's gonna roll, it's gonna come over here, and it's gonna come to rest about right here, right? Won't it?
Yeah.
And that's why Aristotle said the natural state of things is to come to rest. Because most things will stop moving on their own. So who was right, Aristotle or
Aristotle was right.
Newton? Newton said that it's going to continue in motion. An
Aristotle-
object in motion stays in motion.
Aristotle understood it as it applies to Earth.
Good. Aristotle was, this theory of motion was strictly for Earth.
Dude, it says that.
Yeah, it says that. So if you go to the next bullet point, Aristotle's theory made sense on Earth, where there's friction and air resistance slow a moving object to a stop. But in space, his theory didn't hold.
Well, we don't need to get down space. Sure.
Yeah, we live on Earth, dude.
Yeah.
So I want you to with your neighbor, talk and explain both Aristotle and Newton's ideas of motion and how they are different. I want you to talk to each other and say how they're different. You may need to review,
Because one of them.
you might want to review Newton's first law and then go back to what Aristotle said. If you're watching the video, think about that real fast. Okay, so let's bring it back up here, guys. You've had some time to talk about their differences.
Go fast.
Let me summarize the differences, then we'll move on. Aristotle said that the natural state of things is to come to rest. Newton, if you contrast that to Newton, he said that an object will remain in motion unless it's acted upon by a net force. So, let me see if I can illustrate this. If you push this ball, say you give it a good shove. Okay, well, it's going to move across the ground, and it's going to end up over
Yeah,
here.
but it's going uphill.
That's level ground. How come, Clint? How come Newton was right and Aristotle was wrong?
Because
Isn't this ball naturally coming to rest?
But it's acted on by
Good. What other force is acting upon this ball to stop it?
friction.
Yeah, you put a force to the right by pushing it, but there's forces to the left called friction and air resistance that are stopping it. Right, guys?
Yeah, that's right.
Isn't, when I push this ball across the counter, isn't friction acting on it that way?
Yeah.
And it's slowing it down. And air resistance is slowing it down too. So, okay, I'll wait. Clint. So I'll wait. Thanks, Trevor. So Newton was right. An object will remain in motion unless it's acted upon by a net force. There's a force acting to slow that ball down. That's what Aristotle didn't realize at the time. There was a force being used to stop it. That's why it came to rest. In space, though, if you throw a ball into space, it's going to keep going for how long?
Until
there's a net force that hits it, right?
Yeah.
And so, hopefully that makes sense. How Newton chose to view motion is more correct. Okay, let's go back to Newton's first law. An object in motion will stay in motion at constant velocity. An object at rest will remain at rest unless it's acted upon by a net force. So, forces cause all motion. This might be the most important bullet point of the whole chapter. Forces cause all motion. If you want something to move, what do you got to do?
Force it.
You got to put a force on it. You got to put a force on it. Every time the motion of an object changes, it's because a force has been applied to it. So if something slows down, is there a force being applied to it?
Yep.
Yep. If something speeds up, is there a force being applied to it?
You bet.
Yes. So what exactly is a force? Guys, this is the best definition that I can come up with, and it's simple. A force is a push or a pull on an object. It's that simple. You push or pull it. The SI base unit for force is called the Newton. It's abbreviated with a capital N. And yes, it's named in honor of Isaac Newton. So the unit of force is called a Newton. We're going to talk about Newtons for the rest of the year. Let's go into a little bit more detail about what a Newton is. A Newton is the force needed to cause the mass of 1 kilogram to accelerate at 1 meter per second squared. Let's put that in terms of something that we could understand. 1 kilogram is like 2.2 pounds. So it's the force needed to move this 2.2 pound object to accelerate it at 1 meter per second squared. Is that very much force, guys? Think about 2.2 pounds.
No.
Very small. That's a very small unit to measure in, right? A Newton is a very small number. Let's look at the units for Newtons. A Newton is 1 kilogram per meter per second squared. So we need to be in kilograms. The mass has to be measured in kilograms. And then acceleration is measured in meters per second squared. Kind of strange units here for a meter, but that's what it means. Okay, again, let's put it in something in terms that you might be able to better identify with. 1 Newton, guys. 1 Newton of force is equal to the weight of a medium-sized apple.
That's going to be.
Okay, a medium-sized apple. The weight of a medium-sized apple is about 1 Newton. Or if you want to think about it in terms of a hamburger, it's the weight of a 1/4 pound hamburger. So here's a medium-sized apple. Does it take much force to lift it? No. That's 1 Newton. Okay? Here's Newton's apple right here. It's foam, so it's much bigger. It's less dense. But I'll pass this around. You can see how much 1 Newton is. It's calibrated to exactly equal 1 Newton worth of weight.
Nice.
Okay, forces. A force is a vector quantity. You're supposed to write that. It's a vector quantity, not a scalar. It's a vector, which means that it has both a magnitude and a direction. A force will have a magnitude and a direction. It's common to represent forces using diagrams in which a force is represented by an arrow. We're going to do this later on today. We're going to draw these diagrams, and forces are going to be represented by arrows. And again, guys, the length of the arrow is proportional to the magnitude. So the longer the arrow, the stronger the force. Larger forces have longer arrows, smaller forces have shorter arrows. Here's an example. If this arrow represents 10 newtons of force, how would I draw a vector that's 20 newtons of force?
Double that size.
How would you draw it, though?
Twice as long.
Twice as long, because it's twice as big. I don't know if that's twice as long. Close enough. Is that twice?
Yes.
Pretty close. Okay, so remember, the length of the arrow tells you the magnitude, so it does matter. For the next 10 or so minutes, we're going to go over different types of forces. Yeah?
Why are they called fig Newtons then? That was his brother Fig.
Okay, Clint. Yeah, good question. You should look that up, Clint. Let us know what you find out. Okay, we're going to talk about different types of forces. There's two main types of forces. Number one is contact forces. This is where you actually have to physically touch the other object in order to transfer the force. And then there's action at a distance forces where you don't actually have to touch that object in order to transfer the force.
It's a really creative name.
Yeah. Action at a distance forces. Okay, let's talk about contact forces first. Contact forces are forces that result from the physical interaction between two objects. So you have to physically interact, touch each other. Here are the contact forces we will study. I'm going to go quickly through these. Please be writing them down fast. Frictional force. Physics textbooks will abbreviate frictional forces like this. They use a capital F for force and a subscript lowercase f for friction. So you would read it as force of friction. Force of friction. That's a contact force. You have to touch in order for friction to work. Another one is tension. Tension force. Some physics textbooks represent it like this. We have capital F and a lowercase or a subscript t. But I like to represent it, and a lot of other physics textbooks will represent it with a capital T. Please make that note. If you see a capital T that I've wrote, that means it's a tension force. Number 3, normal force. We'll talk more about each one of these in more detail, what a normal force is. But here's how they represent a normal force. Or, a lot of textbooks will just put a capital N, and that's how I like to represent a normal force. So if you see a capital N, that means normal force.
But that means Newton.
But it does mean Newton as well, yeah. Yeah. Okay, number 4, air resistance. The force of air resistance is represented by capital F with subscript air written under it. And that's how I do it too.
That looks like
Okay, number 5 is an applied force. This is a very important, you're going to see applied forces all the time. An applied force is given the symbol capital F for force and then applied, either written out or abbreviated as a subscript. And then finally, a spring force. Capital F for force and then spring written as a subscript underneath.
Is there no winter, summer, or fall sports?
Huh.
Carson, that's a good one. All right, contact forces. You have to physically touch the other object for these forces to be transferred. Does that make sense? Okay, now let's talk about forces at a distance. Forces at a distance are forces that objects feel even though no physical interaction occurs. We're going to study 3 of them. First one is called gravity. Gravity acts on something. There's no physical interaction there, but it will act on everything even though it's not physically touching it. Okay, I represent force of gravity like this. force, capital F, sub G, force of gravity. But isn't that the same thing as weight, guys? Isn't weight a force of gravity? So a lot of physics textbooks, and I'm getting in the habit now of writing it like this, the capital W. So please make that note in your books. Force of gravity is equal to weight. They're the same thing. You can use them interchangeably because they mean the same thing. Okay, electrical forces. We won't study these for a few more months, but here's an example of an electrical force. If you have a proton and you bring another proton close by and then let go of both of them, what's going to happen?
Repel.
They're going to repel each other. Even though they're not touching, there's that electrical force, that electrostatic force that's pushing them apart. And that would happen, of course, with two. If these were electrons, they'd push apart. What if it was a proton and an electron?
They'd hug.
They'd hug. Yeah, they'd be attracted to each other. Yeah. Okay, and then there's magnetic force. We've all played with magnets before. Do we have to touch another magnet in order to move it? No, that force acts at a distance. So the magnetic force. Those three are the forces that act at a distance. Okay, let's talk about direction of these forces. Which direction do they act? An applied force is a force that is applied to an object by a person or another object. So I've got a diagram here. This lady is pushing this box, this red box, across the floor, it looks like. The applied force is going in the direction that she's pushing it. So it looks like to me she's pushing it to the right, so I would draw an arrow to the right and write force, apply. But could this go to the left if she pushed it to the left? Sure. Could it go up if she pushed the box up? Or down if she pushed it down? Sure. So which direction does an applied force act? An applied force acts in the direction that you're applying it. Okay? We're going to keep this diagram. Okay? An applied force acts in the direction that you push or pull it. Okay, let's go to force of gravity. It's the downward force caused by the Earth's gravitational field. Force of gravity always moves things toward the center of the Earth. Straight down. So in this case, if we're talking about the box, the force of gravity is going to pull it straight down. And you will write force of gravity like that. Or you could simply write a capital W for weight. Remember, they're the same thing. Force of gravity and weight are the same. Here's an equation that's going to be crucial to know. In fact, I'm going to put a box around it. Force of gravity. How do you find force of gravity? Well, you take the object's mass and you times it by g. Remember that g is the acceleration due to gravity, and on Earth, it's equal to 9.8 meters per second squared. So somewhere by your book on the margin somewhere, put force of gravity is equal to mg. Could you also have written it like this? Weight is equal to mg? Sure. So I'm going to try to use both of them. Force of gravity is also known as weight. Force of gravity is also known as weight. Okay. Which direction does gravity act?
Down.
Down. Yep. Gravity will always pull things straight down. All right. I want to highlight something that's very important for you to understand, and that's the difference between mass and weight. Okay, the mass is how much matter an object has. So if you talk about yourself, your mass is made up of all the atoms that make up your body. If you took the mass of all those atoms and added them up, that would be your total mass, right? The SI base unit for mass is a gram. And so if you look at the periodic table, it tells you their atomic mass in grams. Well, let's contrast that to what weight is. Weight is a measure of how much force of gravity is pulling on you. So it depends on the force of gravity and how much it pulls on you. if you weigh 130 pounds, that means the force of gravity is pulling you down with the force of 130 pounds. So let me ask you this, Rylan. Which one is going to change if you went to the moon? Would it be your mass or your weight?
Your weight,
Your weight. Why? You're right. Why?
because there's less gravity.
Good.
Your mass would change.
Because weight depends on gravity.
Your mass would change.
Your mass,
Bone has
I'm sure you would gain or lose half a gram on the trip to space.
but mass is how much matter you're made up of. Is all of a sudden when you go to the moon, is your arm going to fall off?
No, but what if you lose muscle mass in the shipwreck?
Assuming
No,
the type where they're instant.
yeah. There's some assumptions being made.
See, you can't assume those things.
But the same number of atoms that make up your body here, if you went to the moon, aren't they still going to be there?
Yeah.
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 Okay, we're going to move on.
Yeah, laugh.
But hopefully you understand that weight is kind of dependent on gravity. It will change. Now, what if you went to Jupiter? Would it weigh more or less? A lot more. Why? Because the acceleration, so weight is equal to mg. The acceleration due to gravity of Jupiter, huge. In fact, you wouldn't even be able to stand up, would you? It'd be crushing. It'd be crushing. All right, so weight depends on gravity, which will change depending on where you're at in the universe. So let's answer this question. Which unit, mass or weight, changes with your position in the universe? Your weight does. Again, because of gravity. Okay, so weight in physics is calculated by multiplying the object's mass by the acceleration due to gravity. This is our key equation. Force of gravity, or weight, same thing, is equal to mg. Force of gravity, i.e. your weight, is equal to the mass of the object multiplied by the acceleration due to gravity for that planet. Here's some conversion factors. We're going to do a practice problem here in a second where you're going to calculate how many newtons you weigh. 1 pound is equal to 4.45 newtons, and that's on Earth. 1 kilogram is equal to 2.2 pounds. Okay, so let's remember these conversion factors, because practice problem number 1 says calculate your weight in newtons. Now we calculate our weight here in the United States with pounds. So in order to go to newtons, you need to go to convert from pounds to kilograms. So let's follow this.
You just told us what 1 pound is equal to, though.
Okay. Weight is equal to your mass in kilograms times by the acceleration due to gravity. So let's try this. On your books, you're going to convert your pounds to kilograms and then times it by 9.8. Does that make sense? If you're watching the video, I'd like you to hit pause and try that first, and then before you continue on, and we'll show you the answer.
$150. Do that.
Should we do 150? Okay. Let's assume that you weighed 150. Okay? 150 pounds. LBS is how you abbreviate pounds. Put that over 1. Now, they gave us a conversion factor. 1 kilogram is 2.2 pounds, so let's use that. If pounds is on top, where's pounds got to go? Bottom. And in the conversion factor, it said 2.2 pounds was equal to 1 kilogram. So my pounds will cancel out, and I'm left with kilograms. So 150 divided by 2.2. And that's 68.2 kgs. Now, if we wanted to know how many newtons that would be, we got to get a force on it. So weight is equal to mass times g. The mass is 68.2 kilograms. And let's times that by g. What is g on Earth, guys?
Negative
9.8 meters per second squared. Okay? So we take that number times it by 9.8.
Would you put it negative?
Okay, good question. Hold that thought for a second. So weight,
Can't weigh negative.
is equal to 668.2 what? Newtons. Remember the units? Kilogram, meter per second squared. That's what a Newton is. Okay, good. Cole, you had a good question. Wouldn't that be negative 9.8? And the answer is yes, because gravity is always pulling down, right? But
So then your weight would always be negative.
can we just understand that that's always going to be pointing down? So I think it's understood here that if we keep it positive, we know that the direction is down, right? I think that's just the assumption that we're making. Okay. Let's talk about direction of forces and continue with the normal force. This is a very important force, so let's talk about it. Again, I will abbreviate normal force with a capital N. It is the support force exerted upon an object that is in contact with another stable object. It's a support force exerted upon an object that is in contact with another stable object. An example of this is a book on a desk. So if I draw a desk right here, and here's my book. Okay? Well, let's draw the forces that are exerted. Isn't force of gravity pulling that book down, guys? Its weight is pulling it down. But is that book moving down? No. So there must be some force that's counteracting it or balancing that force. That force, in this case, is called the normal force. So again, it's the support force exerted upon an object that is in contact with another stable object. I want to focus on this question down here. Which direction does the normal force act? In this case, which direction did it act? Oh, it acted straight up. Will it always point straight up? No. Here's the answer to this question. The normal force acts perpendicular to the surface that it's on. It acts perpendicular. What does perpendicular mean? This is the sign for perpendicular. Okay? It forms a 90-degree angle right here. That's what perpendicular means. So in this case, perpendicular to the desk is straight up. But what if that book was on a surface that had an angle? Now let's draw force of gravity. Force of gravity is going where? Straight down. Where would normal force point? Perpendicular to the surface. So in this case, it's going this way. So again, the normal force, the direction can change. It's perpendicular to the surface that it's on. Okay, let's talk about friction for a second. Friction is the force exerted by a surface as the object moves across it or makes an effort to move across it. So force of friction, again, I will abbreviate it with a capital F with a lowercase f as a subscript. Okay, now let's talk about this one down here. Which direction does the force of friction act? In this case, this lady is she's putting an applied force on the box to the right, so friction acts to the left. But here's a better way of saying which direction friction will act. It always acts opposite the direction of motion of the object. Doesn't it always oppose motion? Yes?
Yeah.
Friction. It always opposes motion. So it always will point in the opposite direction that the object's going. Hopefully that makes sense. Okay, there's a couple more. Let's talk about air resistance. This is a special type of frictional force that acts upon objects as they travel through the air. So air resistance is really friction in the air. So if this is a ball that's falling down, we've got gravity pointing down, but there is some air resistance pointing up because it's like friction. It acts in the opposite direction of the object's motion. Gravity, notice that the length of this vector is much longer than air resistance, so it is being pulled down. So which direction does it act? Opposite the direction of motion. Okay, force of tension. This is a force that we're going to study in great detail later on. Force of tension, I abbreviate it with just a capital T. It's a force that is transmitted through a string, rope, cable, or wire when it is pulled tight by forces acting from opposite ends. We see tension everywhere. If you look around, you're going to see tension forces everywhere. Here's an example. Say this is the ceiling and this is a light. This is a light that's being hung from your ceiling in the kitchen. Okay? The light has weight. Doesn't it have weight?
Yeah.
mg, we could figure out what that weight was. But it's not moving down. Why is it not moving down, the light? There must be another force that's acting opposite of its weight or gravity. What do we call that force? Tension. So in this cable right here, we call that tension, and it acts in the opposite direction of the weight. Well, it would act in whatever direction this cable, string, or rope, or whatever it is facing. Okay. All right. Spring force. Spring force is this force exerted by a compressed or a stretched spring upon any object that it's attached to it. So I've got an example here. This top diagram shows the spring is at equilibrium. What does that mean, guys? It means it's not stretched and it's not compressed. It's just at rest right here. It's just at equilibrium. Now, the spring can put a force on an object, but you either got to stretch it or you got to compress it. Let me see if I can move this out of the way for a second. So if you stretch the spring, now the spring force is going to want to go back in the direction of its equilibrium position. So it's going to, if you stretch it out, it's going to want to come back and spring back toward its equilibrium position. And just the opposite, if you compress a spring, it's going to want to spring back in the direction of its equilibrium position. Springs are very useful in applying a force. If you think about your garage door at home, the garage door is very heavy. It's not, you know that little motor on the ceiling of your garage, that's not lifting the whole weight of that garage door. You'll notice a big spring across the top on the inside of your garage. That spring gets compressed, and that's what helps lift the door on its way up and catch it on its way down. Okay. You guys still with me?
Yeah.
No.
No? Okay. This next part, I've only got about 10 minutes left, guys. Stay with me for 10 more minutes, we can get through this. This is a very important part we're going to be using the rest of the year. It's called free body diagrams. Free body diagrams. Now, I don't want to say that or write it out every time, so it's abbreviated. FBD. So when you see FBD, you know we're talking about free body diagrams. Right, Jason? Jason? There you are. Free body diagrams. Be writing this in your book. Okay. They are diagrams used to show the relative magnitude and direction of all the forces acting on an object in a given situation. A box is used to depict the object being acted upon by the different forces. So I don't care what it is that we're talking about, whether it's a ball, whether it's a person, whether it's a truck, whether it's a tree, or anything else. In a free body diagram, we use a box to represent that object. So this box right here, well, it might be a ball, it could be a truck, it could be a person, it could be a building, it could be anything, but we're going to use a box to represent that object. And then what we do in the free body diagram is we draw the vector arrows for all the forces acting on that object. It might be force of gravity straight down. We might have an applied force. We might have normal force going up. We could have force of friction pointing to the left. Okay. Practice problem number 2. It says draw an FBD. What is an FBD, guys? Free body diagram. For a book that is at rest on a tabletop, be sure to include all the forces acting on the book. I'm going to do this one with you, and then you guys can try the other two on your own. Okay, this is not the free body diagram. If you were to draw the desk and the book here on top of it, that's not a free body diagram. So let's draw a free body diagram over here. What do I draw to represent the book? A box. Okay? You can put book in there if you want to. Now let's list all the forces that are acting on this book right here. What force is acting down?
Grab.
Okay? Grab. Okay. Force of gravity is acting straight down. Now, we know the book is not moving down, so there must be a force that's counteracting or balancing it. What is it?
Norm.
The normal force. And guys, the length of these two arrows, these vector arrows, should be what? Equal. It should be the same, because the book's not moving. Is there any forces acting left and right here, Jason, on this book? No, it's just sitting there. That's your free body diagram for a book on a table. Practice problem number 3. This one's yours. It says, draw the free body diagram for a girl hanging on a bar that is suspended motionless from the ceiling by 2 ropes. Be sure to include all the forces acting in this situation. Now, if you're watching the video, hit pause, try to draw the free body diagram on your own. And we'll come back in a second and see if you got it right. Okay, so let's see if we got this right. Before I draw the free body diagram, I want to draw what's happening here. So that's the ceiling. It says she's hanging from a bar suspended by 2 ropes. So here's my 2 ropes. Here's the bar that she's hanging onto. Let's draw the girl. And she's hanging onto the bar, right? Isn't that what's going on, guys?
No.
Yes. Now let's draw the free body diagram. We don't draw the girl. What do we draw to represent the girl? A box. Okay, this is the girl. Now, I always like to start with the easiest force to remember. What's pulling her down? Gravity. I put force of gravity last time. It's also known as what? Weight. So I'm going to put W. I'm going to go try to use W and FG interchangeably here. Okay, so force of gravity down, or weight. What's then counteracting that or balancing that force?
Tension.
Yeah, there's tension in these ropes, okay? How many ropes are there? There's 2 of them, so let's draw both of them. So I'm going to draw, now,
They have to be
half the length of this one. Why half? Because now there's 2 of them. So this is tension here, and this is tension here. Okay, and this would be your free body diagram for that situation. Is there any forces to the left and right?
No.
No. That's it. Yep.
You're gonna like number 5.
Okay, number 4. Give it a go. See if you can get it. I'm going to pause the video. If you're watching, hit pause. Try it first on your own, and then watch the video. That's where you're going to learn.
Yeah.
Okay, let's see if we got this one. An egg that is free falling from a nest in a tree. Okay, what do we draw for the egg?
Box.
A box. You can label it if you want to. What's pulling that egg down?
Good old grab.
Good. It's weight. But in this case, I'm going to put force of gravity. Same thing. Now, is there anything else that we should put on this one?
Air resistance.
Good, yeah. Now, if it's falling down, what can you say about air resistance?
It's not
Yeah,
in.
It's going out.
It's not as
It's not as long as this vector, right? So how do we represent air resistance?
there.
Force of air. Now, is there anything going left and right?
Right.
Nope.
Supposed to say that.
It's falling straight down from the tree. So there you go. That is your free body diagram. Okay, is this the last one?
Yes,
Yeah.
ma'am.
This will be the last one on this video. Let's see if we can do it on your own first. So please hit pause. Try it on your own and see if you can get it right. Okay, let's see if you got this one right. So it says draw a free body diagram for a box that's being pushed across the floor. So before I draw the free body diagram, I always like to draw the situation. Okay, so this guy is on the floor. He's pushing this box. Let's say he's pushing it to the right. I know it didn't say that, but let's say it is going to the right. Now let's draw the free body diagram for the box. Okay. In this case, we draw the box for the box. What force is acting straight down? That's the one I like to start with always.
Grab.
Yeah, force of gravity, or weight. It's going straight down. Now, it's not moving down because it's on the ground. So there must be a force that's counteracting or balancing. What do we call that force? That's the normal force. It's got to be about the same length as that vector. And I just put N for normal force. Okay, let's do the forces left and right. He's pushing it to the right. What do we call that force? Force what? Force applied. It's an applied force.
Yeah.
Now, is there any other forces?
There is.
Yeah, the ground is putting a force on the box called what?
Friction.
Yeah, the force of friction. Force of friction. Are there any other forces acting on this box? Okay, yeah, if you want to get technical, there might be a little air resistance, but it's going to be pretty negligible, won't it? It's going to be pretty small. So I'm going to leave it off. Air resistance will leave off almost all problems. It's pretty hard to calculate air resistance anyway. Okay, does that make sense, guys? Free body diagrams. Okay, before I stop the video, did you learn the difference between Aristotle's theory of motion and Newton's theory of motion?
Yes.
Okay. Did you learn all the contact forces?
Mm-hmm.
All the forces at a distance? Okay. Did you learn the difference between mass and weight? Yes. Did we learn how to calculate the force of gravity? How do you calculate force of gravity, guys?
MG.
mg. Force of gravity is also equal to what? Weight. So you could write it like this. Weight is equal to mg. Okay. Did you learn how to draw free body diagrams?
Yes.
Okay. Draw a box, put all the arrows on there with all the forces. And so hopefully you did. You now know enough to do a worksheet in your workbook. Let's go to page, well, it's called Recognizing Forces Worksheet. So please complete the Recognizing Forces worksheet in your student workbook.
What?